The purpose of our work is to study more in depth some topic of our robotics course. We want to take laws, properties, and characteristics seen on lesson and demonstrate and explain them with a deeper study and with MATLAB simulation. We have chosen three main arguments: forward and reverse kinematics, inverse kinematics problem with Jacobian matrix, inverse and transpose, and the problem of redundancy. For this study, we have chosen two types of manipulator: three-link planar arm, that is a two-dimension manipulator with three parallel revolute joints, and a spherical robot, that is a three-dimension manipulator with two revolute joints, one vertical and one horizontal, that can rotate by 360 degrees, followed by a prismatic one that determines the radial stroke.
First of all, our interest started with the analysis of the direct and inverse kinematics for the spherical manipulator and for the three-link planar arm. At the beginning, we obtained the homogeneous transformation matrix for the spherical and three-link planar arm. And after that, we generated the spherical manipulators through the MATLAB's code, and then we calculated the direct kinematic through the command fkine that led us to get the homogeneous matrix. We used the same process for the three-link planar arm shown here. Later we worked on the problem of the inverse kinematics and we focused on the existence of multiple solutions. Maybe one can think that for the solution of the inverse kinematics it's necessary to use this command, but we found the following error, and that signed the two different solutions for the problem of the inverse kinematics. Anyway, it's possible to solve this problem using the command ikine and defining an array of masks in size 6 by 1. Setting the mask matrix, we obtain a value of QINV that is equal to the joint space Q1. We can use the same process for the three-link planar arm, where the MATLAB's command will be this one. In this case, we must emphasize that the joint space that we got is different from the one that we know as Q1.
We have also analyzed the inverse kinematics algorithm with the Jacobian, and firstly we have taken into account the one that uses the Jacobian inverse. Since the Jacobian matrix must be square and non-singular, and since the three-link planar arm works in the plane, after the Jacob 0 block, we have added a variable selector in order to select the first, the second and the fifth rows, so to have a square Jacobian matrix. By doing this, we can see that all the errors converge to zero, so we have an asymptotically stable system. For what concerns instead the spherical manipulator, since it has only three joints and works in the space, we have decided to use a Stanford manipulator to have a 6x6 Jacobian matrix. We have obtained that all the errors converge to zero, with expectation of the angle about the y-axis, that varies between two values, doing a jump equal to 2 pi. This problem is related in computing the forward kinematics in the feedback loop, because the joint variables coming out from the integrator converge to finite values with a noisy behavior.
After that, we perform the inverse kinematic study also with the Jacobian transpose. Here, a Lyapunov function for the error is selected, and the asymptotic stability is reached if the derivative of this Lyapunov function with respect to time is negative. If we consider a constant reference system x.d equals 0, it results that the Lyapunov function is positive and its derivative is negative, so the system is asymptotically stable. For what concerns the Simulink scheme, also in this case the analytical Jacobian is modeled using Jacob 0 block from Peter Cork toolbox, and after that a simple transpose of the matrix is performed. It is evident that each variable converges to zero, with the exception of the yaw angle, that has an offset error of about 0.4 radians. The reason of this offset is that we start from a given parser without specifying constraints, so the problem of multiple solutions arises. Regarding the inverse kinematic for the spherical manipulator, the reasoning behind such a scheme are similar to the one of the three-link manipulator case. Running the simulation, we can see that the aerodynamics converges all to zero, as expected. This method has the advantage that it is not needed to compute the inverse, so it is less computationally complex than the previous method. On the other hand, it works only for constant reference.
The last point is the redundancy. Our purpose is to verify the presence of the null space for redundant manipulators. When a three-link planar manipulator is exploited for positioning tasks only, it is functionally redundant because it has three joins, but the number of variables needed to describe the task space is just two, x and y. Exploiting MATLAB, starting from a non-singular configuration, it is possible to easily compute the geometric Jacobian. Just selecting the first two rows related with the position x and y, it is possible to compute a basis for the null space with the comment null. We performed a simulation on Simulink to compute the velocity of the end effector just using the differential kinematic equation. Running the simulation, we can see that the velocity of the end effector x dot and y dot are very near to zero. By contrary, the spherical robot we defined is not redundant, because it has three joins, but the number of variables needed to describe the task space is 6, 3 for the position and 3 for the orientation, because we are in a three-dimensional space. If one tried to define the null space, as done before with the three-link planar manipulator, the result is not the same. The null space, given as result by MATLAB, is an empty matrix.